Yes. So thank you. I always like talking to diverse groups about climate change. Particularly, I like talking to people who may not agree with me. I'm not trying to convince anybody. I'm just trying to give people the facts about what the science tells us, and then everyone can make their own decisions based on that. So I like to start off looking at the big picture. So this is 35 or about 30,000 years. About 30,000 years on the x-axis here. And this is temperature in degrees Fahrenheit. I've converted everything to Fahrenheit because you all are Americans. Okay, so if you go back 20,000 years, you end up in the last ice age. And that was essentially a different planet. So if you walked out your front door into an ice age world, you wouldn't recognize it. There was ice covering much of North America. Sea level is 300 feet lower. The collection of ecosystems look completely different animals. Now, I think it's amazing. Let me just ask you, how much colder was the planet during the last ice age? Does anybody want to guess? How much do you have to cool the planet to get to an ice age?
15 degrees.
That's actually close. That's very close. It's actually about 10 degrees. And I want you to remember that. So a 10 degree change in the global average temperature, and let me just emphasize, this is the global average. If you change the global average by 10 degrees, you get an ice age. The planet is completely different. And I think everybody can agree it would be an economic disaster if we went into an ice age. Okay, so if we go into an ice age, it's not like, the economy is going to be running fine. It's not going to be running fine. That would be a disaster. We would remake the surface of the planet. All right, so let's go back to this plot. Now you'll see there's this dip right here. This is the Industrial Revolution, and then we are right here. And so let's put on here sort of the future. So this pink band is the fossil fuel era. It is a brief spark in the long time scale of humanity. It's only going to last a few hundred years. Now, we don't know really how much longer it's going to last. Maybe it'll last a few decades, maybe it'll last a century or two, but it's going to end, and it's not going to last 10,000 years, okay? And so fossil fuels are only going to last a very short time on this geologic time scale. But over that time, it's going to raise the temperature of the planet. You can see what's happening. And this is sort of a middle-of-the-road scenario, one where we kind of phase out fossil fuels over the next few decades, maybe the next half century. If we burn fossil fuels for centuries, we'll get more warming. Point that this is a close-up of this century. Now, I don't plan on living to 2100. I see a few people in the audience who might live to 2100. I always tell my students who are undergrads, you are going to live through this. Okay, so you will live through whether we fall on this low scenario. This is a world where we transition rapidly out of fossil fuels. That's about 4 degrees of warming. Or this is the drill baby drill world, the world where we make an effort to burn every molecule of carbon we can find. And this will give us something like 10 degrees of warming in 2100. And this is not a problem for the future. This is a problem for people that are alive today. Maybe not me, but it's certainly a problem for my kids. It's a problem for undergraduates today. And, people that are younger that plan on, eating right and exercising, they might live to most of this. But this is a modern problem. And the choices that we make now will determine whether we are down here or up here. This is all policy. This spread is all policy. And again, we're sort of on track for this. If you kind of look at the way the world is going, we're on track for something like 5 or 6 degrees Fahrenheit of warming by 2100. So now, a lot of people often tell me, I don't believe climate models. You can't predict the weather in 10 days. Why should I believe climate models? So I could talk for a long time about that. But let me just give you one reason why you should believe these forecasts. So now, this is the observational data. So this is observed temperatures up to 1975. In 1975, there was a paper written by Wally Broker at Columbia, and he predicted the next 40 years of the climate. And that's what he predicted. And if you look at it, that's a pretty bold assertion. If you look at the historical data, you wouldn't use technical analysis and say, well, you're continuing the trend. That actually looks completely different from the trend. And you would only make that prediction if you understand something about the physics of the system. And if we ask how well he did, the answer is he did pretty well. And this is not a one-off. There have been lots of successful predictions of the climate. Let me show you one more I find particularly interesting. This is Exxon. So in 1982, Exxon had scientists studying climate change. And the scientists, again, if we look at this axis, this is year on this axis, temperature on this axis, the blue line, it's in Celsius, sorry, multiply by 2 to get Fahrenheit. This blue line right here is the observations. The dashed line is when they made their prediction. Their predictions are the red dots. So when we tell you we're going to get a few degrees of warming, you should believe that. Now, there are predictions that climate scientists put out that we're not confident in, but global average temperature is one that we are very confident in. So when I tell you we're going to get 5 degrees of warming, if we kind of follow business as usual trends, you should believe that prediction. Now, 5 degrees of warming, you're probably thinking, that doesn't sound like very much. Let's just go over the numbers a little bit. All right, so we've already warmed the climate about 2 degrees Fahrenheit. And we are already seeing impacts of this. So the last summer, I don't know if you remember, there was a Pacific Northwest heat wave. Lytton in British Columbia, Canada, hit 121 degrees, and the next day it burned down. And that is not a joke. We have Hurricane Harvey. People obviously remember that. Sea levels rising. The U.S. Southwest, Lake Mead, Lake Powell, they are literally running out of water. And there are California wildfires. Now, all of these we can connect to climate change. Now, climate change isn't 100% responsible for these. Anytime there's an extreme weather event, something like Hurricane Harvey, there's always at its core weather. But what climate change is it's like steroids for the weather. So, you give a baseball player steroids, all of a sudden he's hitting the ball farther. You add carbon to the atmosphere, you raise the temperature, all of a sudden hurricanes are raining more. They're riding on top of a higher sea. You have more severe storm surge. These are the things that we know are happening. There's an entire field of study called extreme event attribution, where there's a whole theoretical framework for taking single events and connecting them to climate change. So we can do this. We know these events are connected to climate change. And these events are going to be extremely expensive. So you often hear people say, oh, well, we'll deal with it. And we will deal with it. We'll deal with the way we dealt with COVID, sort of incompetence with sort of a lack of empathy, and it's going to be expensive. Climate change is going to make everybody poorer. So let me just give you an example here. So just in Houston, the expenses in Houston, there's $30 billion for the Ike Dike. So the Ike Dike is designed to protect Houston from storm surges coming up Galveston Bay and into the Ship Channel. And then they're also talking about $30 billion to build stormwater tunnels under Houston. And that's to sort of fix the twin problems of higher sea levels, more intense storm surge combined with more rain. And that's also $30 billion. So that's $60 billion just for one city, for one type of impact. There's nothing about extreme heat in here. There's nothing about, all the other issues that are going to arise. It's going to be extremely expensive for us to deal with this. Now, let's talk about some other issues about why, in addition to climate change, why fossil fuels are so expensive. Because when you buy a gallon of gas at the pump, you're not paying the full cost. You're not paying the cost of climate change. You're not paying the cost of air pollution. So fossil fuels kill millions of people every year, and that's extremely well-developed science. So it's basically air pollution, things like particulate matter, ozone, things like that. In addition, fossil fuels are a commodity whose price is set on the global market. Now, the U.S. is largely energy independent at this point. We export actually a little bit more than we import. And so we're net exporters. And there's some issues with that. We're importing, exporting slightly different stuff. But we are energy independent, and yet we're still paying incredibly high prices for gasoline. And the reason for that is that the price of oil is set on the global market. So if you go to West Texas to buy a barrel of oil, you're going to pay the global price for that. You're not paying what it costs that guy to pump it, because he can export it and get the global price. Why would he sell it to you for less than the global price? You're paying the global price. So that means that anything, anywhere, impacts the price of gas at the pump, even though the U.S. is energy independent largely. And so just to give you an example, this shows the price of gas over the last few years. And you can see a bunch of things. You see COVID, price goes down. And then you see right here, and you see this spike right here. And does anybody know what happened to the dotted line? People must know. Yeah, exactly. It's Ukrainian war. So if Putin invades Ukraine, it drives up the global price of oil, and all of a sudden we're paying more at the pump. Okay, and if we look at natural gas, we see exactly the same thing. You see that natural gas is becoming more and more of a globally priced commodity, especially as we continue to build LNG exporting terminals. We will soon be paying the global price for natural gas. And when Western Europe gets cut off from Russian gas, that jacks the price up. We will be paying. And so because fossil fuels is an important point, are a commodity set on the global market, you cannot ever have economic, energy, national security as long as you use fossil fuels. And to be clear, this is not a problem with wind and solar. Once you build a wind turbine, once you build a solar plant, you know what price you're going to pay for the next 35 years. Because you've already sunk the cost in. You don't have this global commodity issue. Now, you do have some commodities in building. You have to buy copper to build the wind turbine. Once you buy that, the price is set. So you don't have to buy a car now wondering, what's the price of gas going to be a year? I mean, nobody knows what the price of gas is going to be next year. But I can tell you what the price of wind energy and solar power are going to be next year. And just to sort of emphasize this, I'll skip over this. It's a enormous. These price fluctuations are an enormous economic risk, okay? Because nobody can plan for the price. So if you're a business owner, you don't know what you're going to be paying for gas next year if you own a fleet of trucks. So you just don't know. Whereas other energy sources are a more predictable energy source would be good for the economy. Oh, and I'll say, I made a sort of a joke here. Headlines will never be written. Texas wind prices skyrocket as energy sector responds to U.S.-Russia tensions. I mean, the price of wind is always zero. The marginal cost of wind energy after you build a turbine is zero. Almost, not quite zero, almost. Saudi Arabia rejects Biden plea to increase sunlight as midterms loom. Again, these are headlines that will never be written. I mean, today, because we rely on fossil fuels, the U.S. president has to go begging to Saudi Arabia to increase production to reduce the global price. I mean, America should not have to go beg Saudi Arabia to increase production. And again, this is because we rely on fossil fuels. It is a globally priced commodity. Now, is there a plausible alternative? Because I would agree with what everybody's thinking is, this all may be true, but we need energy. And that's absolutely right. In fact, there are 2 billion people in the world who live on less than a few dollars a day, and they need a lot of energy in order to lift them out of poverty. So then the next question becomes, is there a plausible alternative that avoids all of these problems? And so there are basically 3 questions that this devolves down to. The first one is there enough wind and solar energy to power our society? So the Earth today, on the Earth, humanity uses about 15 terawatts of power. There are 100,000 terawatts of solar energy falling on the planet. And that's not even counting wind and all the other sources. So I'm not going to talk anymore about this. You can ask me questions about this. There's lots of clean, renewable energy. So then the question becomes, well, we know, and trust me, lots of people come to me and go, yeah, but the wind doesn't, or the sun doesn't shine at night. What you going to do then, smart guy? So trust me, I've heard that before. So the question then becomes, can you produce a grid that always has power? Because we want power, we want to flip the switch, we want the lights to come on. Okay, everybody kind of agrees with that. So can you do that with a grid that runs on intermittent power, which is wind and solar? And believe it or not, there's been a huge amount of work done on this. And I'm not giving you my opinion. I'm going to point out studies that have been done on this. So I'll summarize them, and I'll give you some references right here. So I'll say that there are lots of studies that have been done on this question about how do you design a grid. And I'll explain how you do it in a second very roughly, but I just want to emphasize this is a very well-studied problem. Okay, so this is not a thing that, oh, wait, the sun doesn't shine at night. I mean, we know the sun doesn't shine at night. Lots of engineers at big universities, at government labs have studied this question. So how do you do it? How do you create a grid that always has power, even if the wind and the solar are intermittent? And so the way you do it is you really have two different sources of energy. So let me get out of the way the idea that you would have a grid that runs entirely on wind and solar. Nobody advocates for that. Instead, you have a grid that on average is about 75% renewable, so wind and solar, and 25% we call dispatchable power. Dispatchable power is power that you can turn on or off. So in a current grid, you can think of it as what we call load following. So on a current grid, you have base load power, which runs all the time, and then you have load following power. Those could be natural gas plants, things like that, that turn up and down as the demand goes through the day. So the dispatchable power essentially takes the role of load following power on the grid. Now this is on average. On some days, let me say before we do that, what do I mean by this? Well, renewable is mainly wind and solar. There is a role for batteries on a few hour time scale. And then dispatchable power would be nuclear, hydro, geothermal, gas with carbon capture, and long-term storage. And all of those, nuclear, we know how to build nuclear. Hydro, we know how to build dams. Geothermal, we know how to do that. It's a little bit expensive. Gas with CCS, we don't really know how to do that, but it seems like that's a solvable problem. And long-term storage is something that a lot of people are working on. We don't really have good long-term storage yet, but I believe in innovation, and the market will solve that problem, I think, relatively quickly. So what is this? But this is on average. So what does this mean? So on some days, you get 100% of your power from renewable energy. So for example, in Texas, we get almost 60% of our power on some days from renewable energy. So Texas is almost, we're not that far away from getting 100% of our power on really windy, sunny days. But that's not every day. And so on days when you're not getting a lot of power, you might only be getting 40% of your power from renewables. You're not going to get 0% because you'll have wind and solar, and the odds of them both going to zero is very low. And people, again, engineering groups have done studies where they take the meteorology and they calculate what's the minimum amount of power. And so, maybe you get 40% or 30% of your power. And then the rest of it has to come from this dispatchable power. It also could come from demand response, asking the Bitcoin miners to shut off. Or things like long-term storage, which hasn't really been developed, but might be. In addition, you could also transport from Iowa if you build transmission lines, things like that. And so this is how you do it. You build a grid that mainly runs on wind and solar, but has enough dispatchable power that it can pick up the intermittency. Now, the reasonable thing to ask is, that sounds really expensive. You're essentially building almost two parallel energy systems. You have 100% of your power, you have enough wind and solar to produce 100% of your power, but you also have to have these this dispatchable power to pick up a big load of it when the wind and the solar aren't available. And so then the question becomes, how much does this cost? Because again, nobody wants to see their bills go up. And the thing to understand is that this is not more expensive, and it's not more expensive because solar and wind are so cheap. So just to give you an idea of how cheap they are by far today's cheapest power. So this is from an estimate from Lazard, LCOE's levelized cost of energy. So combined cycle gas is the cheapest natural gas plant, and that's $56 per megawatt hour, about 5.6 cents per kilowatt hour. That's at $3.45 per MMBTU. So it is much more expensive than that today. So today it's $5.50 or $6 an MMBTU, and a couple weeks ago it was $8 an MMBTU. And so onshore wind is $41 per megawatt hour. Solar PV is $40. Now, this was not true 5 years ago. A lot of people are under the impression that wind and solar are expensive energy, and that was true 10 years ago. The price of solar has dropped 90% in 10 years. Price of wind has dropped 70% in 10 years. And the reason is because of massive innovation. If you believe in the free market and you believe in innovation, this is the poster child for how you do that. And I can talk also about innovation and how you drive prices down. Ask me, I won't go into too much detail about it. Now, a lot of times people don't believe this. They'll come up and go, that's bullshit. I don't believe that at all. So let me tell you about what's going on in Texas. So ERCOT, our beloved grid, publishes every few months what they call the interconnection queue. And this shows what people plan to hook up to the grid. So these are projected projects to hook up to the ERCOT grid. And this is the interconnection queue capacity by fuel types. You have gas over here, you have wind, you have solar, and you have batteries. And you see that solar is what people are connecting, and batteries, sort of shockingly. Not a lot of wind, and the reason for that is the wind lines running to West Texas are already full. On windy days, they can't take any more power. But they can still take solar because the wind and the solar tend to be anti-correlated. So when the wind goes down, the sun comes up. And so they're building solar because there is capacity on the lines. And so that tells you that if we built more transmission lines, we would be building a lot more renewable energy. This is really limited by infrastructure. And no one's building gas. And if you go back through the years, there used to be a category for coal, and it was zero for so long, they just took it out. I mean, coal is dead in the U.S. In other places, not quite so much. But this shows you what's happening. And so if you don't believe wind and solar are the cheapest power, look at the people who are trying to make money off it. These are not Birkenstock-wearing hippies who are out to save the world. These are energy guys who are out to make money. And you make money by building wind and solar because the price is basically zero once you construct it. And the way that the ERCOT grid, I won't go into great detail, the way the ERCOT energy market works, wind and solar is displacing everything else. I mean, it's extremely lucrative. Now, again, people have done estimates of what the cost would be. And so this plot shows, so this is one report. This is the Berkeley 2035 report. I won't go into details of it. You can ask me if you're curious about it. This shows the price of energy to get to a 90% clean grid, a grid that runs 10% on fossil fuels, 90%. This is just the electrical grid. And you see that you can get there, and when you get to 2035, you are paying slightly more for energy than you are today. But you're not paying costs of air pollution. You're not paying costs of the variability of fossil fuel price, the fact the price goes up and down. You're not paying any of those. You're not paying the price of climate change, which, again, is going to be incredibly expensive. And so if you factor those in, this is basically what it looks like. This is incorporating these social costs that you don't pay at the pump or at the plug. This is the price. This is the price with fossil fuels. This is the price without fossil fuels. This mainly comes from health, including the health impacts of burning fossil fuels. And I think I can wrap up there. So let me sort of say that climate change is a problem, and it's a problem for people that are alive today. It's going to make us less rich. It's going to make, it's like, how many people here like the weather out there? I mean, seriously. And let me tell you, the bad news is this is the coolest June of the rest of your lives. I mean, not literally, but in 5 or 10 years, you're going to look back at this. You're going to go, that was cool. I mean, it's just going to get worse. And you're running your air conditioner more. You're a prisoner in your house. If you have kids, they don't want to go outside in the middle of the day. I mean, you don't want to live in a world that has a lot of climate change. You don't want to live in a world that has a lot of air pollution. You don't want to live in a world where Vladimir Putin has his knee on our neck because he controls the price of oil. And that's essentially the world we live in. But we don't have to live in that world. We can build a substantially fossil fuel-free world. Now, we can't do it tomorrow. It would take a few decades, but you need to start sometime. And if you don't start now, it'll still take a few decades. If you start in 20 years, it'll still take a few decades, but it'll be a few decades from when you start. And we can do it at very low cost. I mean, it's not like you're going to see this, it's going to bankrupt America. Anyway, I will wrap up there, and I'm happy to answer questions in the